A dormant seed exists in a state of suspended animation. It can wait in the soil for years for the right combination of moisture and temperature to trigger its first signs of life. The success of that sprout depends on the specific ions dissolved in the surrounding water. These compounds determine whether a seed hydrates and begins to grow, or undergoes a catastrophic failure at the cellular level. To observe this interaction, we are testing seeds across 4 distinct liquid environments: normal tap water, distilled water with 0 dissolved solids, a sodium chloride solution, and a solution treated with potassium nitrate. The dissolved compounds in each of these liquids will mechanically alter the seed's ability to sprout, revealing how different chemical concentrations program the plant's development before it even leaves the soil. We begin with a baseline of normal tap water. This contains total dissolved solids, minerals like calcium and magnesium that interact with the seed's internal chemistry to allow for healthy hydration. Using highly purified distilled water with 0 parts per million of dissolved solids actually creates a problem. An environment completely stripped of minerals causes a cellular imbalance, often stalling the seed's metabolic start. This discrepancy is visible in these kidney bean seedlings. The right sample received standard minerals, while the left received distilled water. The mineral-rich seed grew to 14.8 centimeters, while the distilled water sample reached only 11.2 centimeters. The data suggests that seeds require a baseline level of dissolved minerals to properly initiate the high-energy process of sprouting. While a lack of minerals stalls growth, an excess of the wrong minerals is destructive. Our third liquid, a sodium chloride solution, represents the primary environmental stressor for modern agriculture. This creates osmotic stress. When salt concentrations are too high, the liquid acts like a chemical sponge, physically preventing water absorption and dehydrating the seed. If high enough, toxic sodium ions breach the membrane, disrupting the plant's nutrient balance and poisoning internal cells. This chemical attack results in stunted root systems, delayed germination, and in high enough concentrations, the death of the embryo. Salt stress is a dual threat. It simultaneously starves the plant of necessary hydration while actively degrading its cellular structure. To counter these effects, we use our final liquid, potassium nitrate. This is an osmotic primer used to forcefully break seed dormancy in difficult environments. Some species, like buffalo grass, have a naturally tough exterior that prevents sprouting. Treating these seeds with potassium nitrate, seen here as the green-dyed burrs, chemically alters the seed coat to allow for rapid water uptake. Potassium nitrate acts as a shield in saline soil. It floods the system with beneficial ions, repairing membrane damage and effectively repelling the toxic sodium. These primers work by systematically overriding the seed's natural stress responses, allowing the plant to sustain growth even in environments that would otherwise be lethal. This chart shows how the chemical makeup of the water definitively dictates the success rate of the crop. The difference between a failed harvest and a thriving field often comes down to these microscopic parts per million. This technology allows farmers to produce food in saline regions where traditional crops fail. Mastering this chemical balance has enabled the cultivation of 6 million hectares of canola in saline soil, producing 13 million tons of oil annually. Water is a chemical messenger. The microscopic ions within it program plant growth from the very first second of absorption. Friendly, outgoing. Subscribe for more cinematic science experiments and let us know in the comments, what variables should we test in the lab?